Okay, welcome. So this is an announcement about assignment. So please take note. And today we are going to continue our chapter on analytical thermodynamics. So last lecture, so this is a recap for you. So last time, what did we learn? We introduced new functions of states. So namely, we introduced new thermodynamic potential functions, and those are listed here. This is a nice table summarizing what we have learned before. Okay, so we went through quite a bit of details. So the idea is we start from first law. So this is our starting point. We have known this internal energy for a long time, and we learned almost everything about the thermodynamics by slowly and progressively arrive at this point here. So this is the first law and the second law combined for the PV system. So it turns out that for the PV system, there are other useful energy-like quantities, and they are shown here. Those are the enthalpy, Helmholtz function, and Gibbs function, which we wanted a way to systematically obtain them. So one way to do this is to go through it by some more abstract way. For example, you can think of the way to obtain these thermodynamic functions as some kind of transformation. Okay, so this is the Lec10 transformation, and that will give you a way to obtain this. Okay, so that is probably the most systematic way that I can present to you. And now this material, I gave you this material at the end of last lecture. I told you those are not going to be in the exam. But you can also trace back to my presentation, and you will see that I kind of also give you a different viewpoint for you to understand how to define, for example, enthalpy from U, the internal energy. So I have U and I want to get to H. Why do I want to do that? The reason I want to do that is because I want to have different natural variables. Okay, so this is one way to look at the problem, and in order to get this, an obvious way, actually, this is kind of straightforward. An obvious way is to add something to it, such that I can have proper cancellations. Okay, so we got our internal energy, the enthalpy, the Helmholtz function, and the Gibbs function, and they all have different natural variables. And the first derivative will give you the first derivative of these potential functions will give you the corresponding variables. Yeah. Okay, it depends on which function you write. So the temperature, for example, if you have a constant volume condition, something you know very well, and if you take the derivative with respect to entropy, then you get the you get the temperature. And if you don't like constant volume, you like constant pressure instead, you have to do your analysis by using the enthalpy. Okay, so these are something we have. And if you can take the first derivative, you can go one step further by taking the second derivative, and that will give you this Maxwell relation. So this is again something we already saw. Okay. So these Maxwell relations are very powerful. You will be able to solve a lot of problems very quickly. And the point is, you should not memorize this. Okay, you should try. You should memorize something, and that something really is here. You really need to know this one. Okay, this one is too fundamental, so everybody should really remember. And then you kind of need to understand how to which natural variables you want to choose, and the rest really is something you can derive very quickly. Okay, so that is the M. So we have got so far, and what else do we need to do? So what we need to do really is to quickly attach some meaning to this these guys here. What do we why do we need all these different potential functions? So this is really the question we should ask today. Okay, so by the end of today's lecture, you will see the usage of them, and you will see they are useful for discussing thermodynamic equilibrium. And when we talk about equilibrium, we also need to talk about the constraints on the system, on your thermodynamic system. And then you will see different thermodynamic potential functions will play different roles according to how you choose the constraints. Okay, so this is the end result which we want to reach today. Okay, so just very quickly, let's ask ourselves, what is the meaning of all this? Why is it so? This is a very thick pen. Okay, so the easiest one is the internal energy U. So the internal energy U. So du is TdS minus PdV. And what can we learn from this? We learn from this the first derivative. Okay, I already show you in the table, so I will just write it. You know how to get them. Okay, we can get the temperature, and we can get the pressure once we know how to write down the du. Okay, so there's the pressure is given by this. Okay, now the most straightforward interpretation of this is if we look at an isochloric process. Then you have a constant volume, dV is 0. And you have du, this is V, this is really V, and this is U with a tail. So according to the first law, this is only TdS. Okay, so now you should think of it this way. If I give you a system and I want you to tell me a good experiment that you can design, in principle, you can an experiment that you can in principle design to give me a way to measure the change of the internal energy. What do you want to do for me? What can you do for me? Okay. All right. So one thing you can do if you have all the resources is to design a good isochloric process. Okay. So when we get to this point, the next thing you can do is, if I also invoke the condition of reversibility. So if the process is also reversible, now here this is general, right? If the process is a constant volume, I arrive at this point. Okay, if I have a reversible process, you know how to link TdS to the heat exchange in this reversible process. Okay, so let's be very clear. I will label. So if the process is reversible, the heat exchange in this reversible process is TdS. Okay, and we know this. And then and if you further have isochloric process, so I just want to label this for you. You can further write one thing. What is this? The thing that you can write is you can relate this process to heat capacity, CVDT. Okay, so a bit of warning here. So this one, long time ago, you saw this. When we still have face-to-face lecture, you saw this. The du is CVDT. I gave you a big warning there. I told you that's true for ideal gas. I even say only for ideal gas. What do I mean by this? What I meant back then was, if you have an ideal gas, you don't need all these lines here. You can instantly write down this du is CVDT. If you forget the reason, you should go back and think about this. Okay, so for the ideal gas, you can write du is CVDT instantly. Okay, but if the process is more general, then in order to reach this line, you need all this reasoning. What is the reasoning? First, I need the isochloric process, and second, I need to invoke reversibility, and that will give me this line. Okay, so just be very careful here. Okay, and the next thing is once you get to this point, you can then evaluate the change of delta U. Okay, so if you can give me this data, if you can measure, if you can design such a process, such an experiment, and you do it slow enough so to make sure this is always quasi-static and reversible, and you will be able to give me a graph, and the graph tells me the heat capacity at constant volume as a function of temperature. Okay, and that gives me directly the change of the internal energy by integration. Okay, so this is a very straightforward interpretation. This is also in Blundell and Blundell. In Blundell and Blundell, you see this line here. The meaning is, I will write it for you. So you can then look at U, internal energy U. What is the internal energy U? Internal energy U is such that the change, this du, is interpreted as the energy change. Energy change. If you have an isochloric reversible process. Okay, so this is the interpretation. How do you extract the change of U? And this is one way. Okay, and therefore naturally we don't need to do that, but you can believe this can be done. Actually, the step will be the same. What is the corresponding meaning for H? Enthalpy. Okay, given that you have done your assignment 1 and 2, you will know there's a parallel between volume and pressure, and I can instantly write this down. So dH, suppose you design the experiment in a chemistry lab, for example, such that the process is isobaric and reversible, and that will give you a recipe to read out the change of the enthalpy. Okay, so in a very, very similar way, so this delta H, the change of enthalpy, can be obtained from the integration like this. Okay, so this a very similar way. You can, if you are not sure about this, you can read Blundell and Blundell. So for example, I'll give you the page number. This is the second edition, Blundell and Blundell, page 173. Okay, now this is okay. These are already kind of familiar, but something which is a little bit less familiar is the other two. Okay, so I will discuss F. And F is a Helmholtz function. Okay, so what is the meaning of Helmholtz function? And Gibbs function, I won't say too much. That is because the entire chapter on phase transition, you will see this Gibbs function a lot. We are going to use it heavily because this is a very good thermodynamic potential functions for us to discuss phase transition. So you see that enough. So I will just complete this part by talking about Helmholtz function. Helmholtz function F. Okay, F is U minus TS. This is our definition. Okay, and you saw it before. And the differential form is this minus dF is minus S dt minus P times dV. Okay. And the usual one, the first derivative S can be obtained from the first differential, and P can be obtained from the first differential. You have seen it. Okay, so now look at this. We can also ask the same question. You have this freedom to design an experiment. What can you do to give me a meaningful change of air? So one way to do this is to look at the isothermal process. This is kind of good because you recognize something for the PV system, right? So here, if I have an isothermal process, something which is reasonable to design, then I will have my dF. dF will be minus S dt. This is sorry, isothermal minus PdV. Okay, so this PdV will have a nice interpretation if I follow the same logic. Now I will plus reversibility. So if I have a reversible process, reversible isothermal process, this PdV has a very straightforward meaning, and that is the work done. So in this case, my the work done on the system, right? Minus sign. This is on the system. Reversibly is exactly P minus PdV. Okay, so I can write this. D work is exactly minus PdV. Okay, so that tells you how to increase the Helmholtz function. So the way I can do this is I can use work. I can use work to increase the Helmholtz function. So for example, when I perform work, volume my change, right? This is how I perform mechanical work. Then I will have this straightforward result. Okay, but what do you, how should you see this? The way you should see this is, if I do work, I can change the Helmholtz function, and that is also a good way to try to understand why we call these potential functions, right? So this is a good way to think about this is go back to your mechanical system, right? When you learn mechanics, let's say you have a spring. You have a mass and a spring system, and you perform work on this mass, and you compress the spring. And where does the energy go? The energy goes to the energy gets stored in some other form. Okay, and that some other form turns out to be the elastic potential energy of the mass spring system. And here you have something very similar. You perform work on the system. Where does it go? It goes to the Helmholtz function. Okay, so the Helmholtz function can change here. So this is something that you can later retrieve, just like the elastic potential energy, which you can later retrieve for moving your block back. Okay, so this gives you a way to interpret this Helmholtz function. So I'll give you a statement here. So in the more general case, what do we have? More generally, we have this reversible process. Okay, so I will still want to stick to the reversible case. If I have a decrease in F, the decrease in F, so which means delta F is negative, and that decrease, this amount is the same as the maximum energy, that can be free What is the condition for this? This is isothermal process, right? So I use maximum, right? So I will finish this. So that can be free in an isothermal process. And met available for what? For useful work. Okay, now that is why very often when you see people talking about Helmholtz function, they use the term free energy. So that is this is the reason, okay, which is the energy which is useful for work. Okay, so this is this leads to the notion of Helmholtz free energy. Okay, now here, this is a very general statement. Where is the, which part is general? The part which is general is also related to the usage of work maximum. So if you use this kind of term in thermodynamics, by now you know this involves some kind of inequality. Okay, so that is why it's a general process. And you can see here, the word reversible disappears. Okay, so now everything is connected. If you have a general process, you don't know whether it's reversible or not reversible, you better assume this is not reversible, and therefore you have to attach an inequality somewhere, and that inequality will give you this kind of a description, whether it's a maximum or minimum. Okay, and that is why you have this very general statement, and the inequality in the end will be something like this: d bar w. This is the work, the useful PdV work is related to the Helmholtz function by this inequality. Okay, so if I have a reversible process, I would take the equality sign, and that is what I discussed up here. Okay, so my d bar d bar w will become d bar w reversible, and that will then allow me to take this minus PdV. Okay, otherwise I will have this statement. Okay, and that is the interpretation of the Helmholtz free energy. Okay, now let me try something. Let me try to give you this. Okay, so let's see if we can write this down, and how do we set up the argument for us to reach this point. And again, at this point of the course, even if you don't know the precise step, you should have some general feeling about how to introduce this kind of inequality. And the way to do this is to invoke the second law. So second law is the law that involve all this inequality, right? So that is a way for us to discuss a general case like this, and try to give this result. Okay, let me try. Okay, so what is the color? Yeah. Okay. I will set up the system. I will consider my system like this. I will consider a system that can exchange energy with a surrounding, energy with the surrounding. And I want to fix the temperature. I want to still talk about isothermal process. Fixed temperature T. Okay, so now I have a system. I have a system, and then I have my surrounding. surrounding, and then the rest is closed. Okay, so this is my universe, and therefore I will apply the second law, and what I can say is that the change of the entropy for this thing, this whole thing, is greater than or equal to 0. Okay, so I will just split this out. I would then say I will write the change of entropy for the system plus the change of the entropy for the surrounding. This is my ds total, and this has to be respecting the second law. The rest is thermally isolated. Okay. So now I suppose some heat d bar q enters the system, right? I enter the system, so the heat has to come from the surrounding. So if I have this much heat enters the system, what happened to this guy here, the second term? The second term, ds0. This is what you have seen before when we discussed this mass, a small thermodynamic system in thermal contact with the reservoir. You can think of it like this. Actually, it's the same system. It's just we invoke a little bit more constraint. Okay, so you know, in this case, I will have heat leaving the surrounding. So this is the ds naught for the surrounding. So I will have this much heat leaving, and the heat exchange is at temperature T. Okay. And in this case, I can just plug this in. I will have my ds minus d bar q minus ds naught plus ds naught. Ds naught is d bar q divided by t, and this has to be greater or equal to 0. Okay, so this is you can also write it like this. The d bar q is less than TDS. Okay, so now everything with the naught is for the surrounding. So I should label this for you. This is this is the surrounding. Okay, and everything without this subscript is my system. So this is really the result for the system. Okay, now coming back to here, I can write d bar q. Now for the system, I have d bar q is du minus d bar w. First law. This is first law for the system, and therefore I will have du minus d bar w is equal to d bar q. Right? This is a general case. And therefore this d bar q is less than TDS. This sum of these two terms must be less than TDS. Okay, so let's rearrange. I will have du minus TDS. This has to be the same as this, right? So I just move terms around. And I have an isothermal process up here, isothermal. And therefore, I can move this T inside the differential. Okay, this thing has to be less than d bar w. But what is this? This one is du minus Ts. This is exactly the definition of df. Okay, and collect all the terms. This will be less than d bar w, which is what I want to show you here. Okay, so where is it? Okay, so this is what I want to show you. Okay, and this is how we can set up the argument to reach this point. So for the general case, you have this inequality. For the reversible isothermal process, you have the equality part of this last line here. So this last line is the result I want. It also tells you the meaning of free energy as discussed in my previous statement. Okay, so let me, where is it? This one should be here. Okay, all right, next. Gibbs, I will not say too much. I have something in the note, but we will see a lot next week. So we will go back to that. We will discuss Gibbs when we discuss phase transition. Okay, so the interpretation is kind of cool. Here, if you have dF equals d bar W, that is I will write, so dF equals d bar W for reversible isothermal process, and the work done on the system is used to increase the Helmholtz function. That is why this is called the free energy. If you think about this spring and the block system, you perform work on this system, you use to increase the elastic potential energy of the system. You store it, and then if the whole thing is reversible, no friction, you know you can recover all this elastic potential energy, and then you can use it to drive the block away. And for the thermodynamic system, this is a very similar concept. Okay, so this is also a good time to talk about, to tighten a little bit about this claim. What do I mean by full knowledge? So full knowledge about the thermodynamic system, full knowledge about the thermodynamic system. Okay, so we are going to take Helmholtz as a demonstration. So we will take Helmholtz function to demonstrate this point. We already talked about this. I gave you a mathematical viewpoint last week, I believe, maybe two to three lectures ago. I told you there's an asymmetry between differentiation and integration, and that is how I motivate the free the natural variable. So the point is, if you know any of these thermodynamic potential functions in terms of the natural variable, you know everything about the thermodynamic system. Okay, that is the claim, and I gave you the mathematics last time. Okay, so what is the natural variable for F? This is temperature and volume. Okay, so now for the PV system, what do you want to know? You want to, if I write it this way, what is the meaning? The meaning is, I assume you know your temperature. I also assume you know your volume. That's to say, if you write F in terms of explicitly in terms of T and V, I assume you are able to control T and V and then calculate F. Okay, so you already know F, you already know T, you already know V. That is what I meant by this line here, the first line. And then entropy you can obtain by derivative, right? So the this is in that table. Okay, entropy you know, and you know pressure. So if you have a PV system, you already know everything. So this is minus. But that is not enough. That is not quite enough. By full knowledge, I also want you to tell me what is the internal energy for this system. This is the input parameter. Okay, you input this. Then you can get this. This is all okay. It's straightforward. But then I also want to know the internal energy, and more than that, I also want you to tell me what is the Gibbs function, and I also demand that you give me the enthalpy. Okay, so can you do this? The answer is yes. This is the point. This is the point. If you give it like this in this form, you can really do it. On the other hand, if, for example, I give you a function f, which is explicitly written in terms of s and v, you do not have this luxury. And this is a situation that I will cook up for you in the assignment. Okay, and I told you the reason. The reason is this, right? Last time I told you, if f is explicitly written in terms of s and v, you basically have a differential equation. It's not just a simple function, right? So you need to integrate, and then you do not have the full knowledge, because once you integrate, you will have some function of, this is a function of two variables. So if you involve the first differential of one of the two, you integrate, you have an unknown function, which once you take the derivative, you recover that f, that expression for f. Okay, so those are the mathematics I described earlier, and you deal with this in the assignment. Okay, so how do we do this? So you also know, right? Because you know how to build f. You build f by subtracting t times multiple of t and s. So the product of t and s from the internal energy u, and therefore you can obtain u from f by adding this, right? You can sum up this term. So you know f. As I said, this is the input parameter, and you know your t. T is your control parameter, and you know s. So s is partial f, partial t, with a minus sign here. Okay, so this is how you get your u. Now this is kind of straightforward, but the reason I want to spend time to talk about this is there's a set of equations which is called Gibbs-Helmholtz equations, and is if you have not seen it before, you might not instantly recognize this. So one of the Gibbs-Helmholtz equations is this. U can be written as minus t squared, and then you take the derivative of f divided by t at constant v. Okay, so this is Gibbs, one of the Gibbs-Helmholtz equation. Okay, there are more, so it's a plural. Okay, now this is a very standard way to write this line here. People write it in a very compact form and then give this name. But as I say, if you have never seen it before, you probably won't recognize that this is an identity. So you can go from here to the final result. Right, you can write it in a very compact form. Okay, so this is maybe one thing I would like you to at least pay attention. Okay, and what do I want you to do? What I want you to do is very simple. I want you to verify this, and the simplest way is really just evaluate this derivative. You have f divided by t, so you can have this quotient rule, and then you get to this. You can reverse engineer and get to this point, and you find out this is really the definition of f, Helmholtz function. Okay, so similarly, you can have G can be written as F plus PV. Okay, and then you have the same thing here. Look, you have your F, and then you have your pressure. You have your pressure, and then you have this. Sorry, you have your volume. V. V is your control parameter, and then pressure is related to the first differential you have. Then you can have this partial derivative. And if you look at this, this is a really identical form. You just interchange volume and temperature. Okay, and therefore you just interchange volume and temperature. So whenever you see T, you go to a V and vice versa. So you can have this result. Okay, this is also a Gibbs-Helmholtz equation. And finally, you can have this. This is also you can express this as in a compact manner. So you have minus t square, and then you have a partial derivative like this, and then you have g over t p. Okay, now here, this one, please verify. Please spend some time to verify all of this, particularly the last line here. Try to convince yourself that this is, you can really write it in this form. Okay. All right. So the next part, which is again, in a very general way, general sense, is the concept of availability. So this treatment about work here, this one, you see, I even have the same diagram. I should have used that more beautiful diagram. I can make it even more general. Okay, so when you make it more general, you have you can also look at other constraint. Now here we are talking about the constraint of isothermal, right? So later we are going to use this availability, the concept of availability, to discuss thermodynamic equilibrium. Okay, and the reason we call this availability can be understood by looking at how the system can give you so the availability, the meaning, the reason this is called the availability is because it gives a measure of the maximum amount of work that can be extracted from the system. Okay, and this depends on the constraint. We actually discuss a special case, and that is the case of the Helmholtz free energy. Okay, so that is the reason why we call this availability, but we are going to use this availability to discuss thermal equilibrium. So I will give you a preview. Here, this is the table from the textbook. Okay, the idea is this. I want to show you that if you have a system which you want to approach thermodynamic equilibrium, if the constraint is, for example, you want to keep the process the process isothermal and isochloric, you want T and B to be constant. What do you want to minimize? What you want to minimize is the Helmholtz function F. Okay, so now you can see there are five. Depending on the condition, you have five different things you want to minimize or maximize. The last line is maximize. So how do we treat this collectively? So we don't need to keep writing this, and that is the concept of availability. Okay, so let's see how to formulate this. Okay, so this is I will set up the problem, and then we take a quick break. and we'll come back to do this optimization. So this is a system surrounded by this yellow part, which we just call the surrounding. Okay, so this is the rest of the part outside this thick line is not accessible to us. So this is our universe. Okay, so this is a very similar setup compared with what I showed earlier. Okay. Okay, so we are going to look at this thermodynamic system. In context, this thermodynamic system, I'm going to design it such that this is in contact with the surroundings. And this surroundings is a special one. So I want to be able to demand a particular value of temperature and a particular value of pressure. Okay, so this will be some constant. That's to say, if I change a surrounding, I will have different T0, different P0. So why is this? Now, can you very quickly give me an example of such a setup? I want a constant P0, a constant T0. How do I achieve this? I see some nice, yeah, it's good. Okay, those of you who have some thoughts, give me a direct message. I think it's kind of important, so you can at least convince yourself that this is not a crazy configuration. Such a system can, for example, be the thermodynamic system can, for example, be my coffee in the cup, and then I open this cup to my office. Right, so in this case, my P0 will be atmospheric pressure, and my T0 will be whatever temperature I have in my office right now. Okay, and this system, I didn't say too much about volume. I didn't say that this system is. I didn't say too much about the boundary. That is intentional because I want this freedom. Okay, so I only demand my surrounding to be kept as P0 and T0. You can even think of this as a huge reservoir that I can keep temperature constant, and this atmosphere is a very good way to simulate a constant pressure condition. Okay, but what I want is to allow work done. I want to be able to discuss work done, just like what I did earlier with the Helmholtz function. So I need to allow. So I allow. What do I allow? I allow volume change. Okay, that's to say this system can shrink. The volume can change. So I can discuss the work. So can discuss work done. And I also want to allow heat exchange. Allow heat exchange. Okay, heat exchange between the system and the surrounding, and outside the surrounding cannot exchange heat with anything else except the system. Okay. So then the question you should ask is what is the appropriate thermodynamic potential to optimize if I want to discuss thermal equilibrium? Okay, so the question is here. Question to discuss equilibrium, thermodynamic equilibrium. What is the appropriate thermodynamic potential function to optimize? that is why this is appropriate time to discuss this. You learn all this thermodynamic potential function. Now this is one application. So the answer then it depends on the your constraint. So the answer of this question depends on the constraint imposed on the system. So it depends on the constraint. Okay, so again, this is this table here. It depends on the constraint, and then you minimize appropriate functions. Okay, so now let's write a few lines for this. So here. Okay, I look at my setup here, this diagram here. So because I can allow volume change, I can allow heat exchange. That is to say, I can allow the transfer of the internal energy. Okay, so I can, in principle, because of these two freedom, these degrees of freedom, I can transfer. I have the possibility of transfer internal energy. Okay, so I can transfer the internal energy and volume from the surrounding, to the system. Right, so imagine if the system is becomes smaller, then the surrounding becomes larger. So that is the meaning of transfer, the transfer of volume. Okay, so I can first look at the surrounding and write the first law. So I will write the first law for the surrounding, Okay, so using the same trick, same note agreement, I'm going to put the 0 to describe the surrounding. So what is this? The first law is just T naught ds naught minus P naught dV naught. Okay. Okay, now I will interpret this first line a little bit more. Okay, so if I will change the I would begin to reduce the notation. So be careful. So what I'm going to say now is this: if I transfer, if I have some change of internal energy for the surrounding, and if I look at this system, this energy, internal energy, cannot go anywhere else except to the system. So du naught is minus du. Okay, I hope this is fine. That's to say we have a conservation of energy. Du naught plus du is 0. Okay, and then the other thing is this volume change. If I transfer some volume from the surrounding to the system, I can do the same thing here. So I can write dV naught is plus, so dV naught is minus dV. Okay, so I can write this as plus P naught dV without the naught. Okay, so this is the same. This is the same as here. So I would just say same. Okay, so now I want to change it to ds naught as a subject. You will know why. So I want to look at the change of entropy. So the rest is just tidy up this line here. So I will have minus du did I make a mistake here? Wait a minute. Minus du, and then I should have a minus P naught dV. Yes, that's correct. That's plus here. Minus P naught dV, and O divided by T naught. Okay, so this is just rearranging. Okay, and rearrange in a better way. I will have this. du plus P naught dV T naught. Okay, so this is just writing the first law for the surrounding. And the entropy change for the surrounding is given by this. Okay, and now I apply the second law. So I will apply the second law to the universe. So the second law, this is the second law. Second law for the universe. So the second law for the universe then say I will have ds for the system plus ds naught for the surrounding. You saw it just 20 minutes ago. So this has to be greater or equal to 0. Okay. And now I plug in this. I will have ds minus this thing du plus P naught dV divided by T naught. This whole thing has to be greater or equal to 0. Okay, so so far, really, we are just discuss this system and we apply first law and the second law. Okay, and then I will have du plus P naught dV minus T naught ds, and that has to be less than or equal to 0. Right, so this is again rearranging everything. This du plus P naught dV to the other side, and then I have this T naught ds to the other side, so I acquire minus sign. So this is correct. Okay, so I'm going to define a new variable. So I'm going to define availability, which takes a symbol A. Okay, and this is U, internal energy of the system, plus P naught V minus T naught S. Okay, so if my system is in contact with a surrounding, and the surrounding has temperature T naught, pressure P naught, this is the availability for my system. Okay, so why do I do it this way? Because if I do it this way, you see if I take the differential, I will have dA. And if I take the differential, I will have dA is du plus P naught. P naught is a constant, so my differential will not see it. And then T naught, again, I will have this Ts. And therefore, this line here is equivalent to dA is less than equal to 0. Okay. All right, so let's take a break. 1:35 now, come back at 1:45, and we are going to use this. Now we do it in a very this is a very simple setup, but then we will be able to get this table. This full table. The table is where is this table? Okay, so my aim is to give you all this by looking at the differential of the availability dA. All right, so see you 10 minutes later. Okay, welcome back. So before the break, we define this new variable, availability. So this line here, the last line here, dA is less than or equal to 0, has the origin of the second law. So it comes from the second law. Okay, so here you should then be able to appreciate the meaning of this differential. Okay, so this comes from the second law, and therefore you can write a little bit more about this dA. This you can learn a little bit more about the change of the availability. Okay, namely, if I know my system, so for a system, approaching the equilibrium, approaching but not yet at the equilibrium. What do we know? We know S of the universe cannot decrease. Okay, so this is always increases or stays the same. It cannot decrease. Basically, it cannot decrease. There is this line here, and therefore this new object, this A, will be decreases, will always decrease. Okay, or stay the same. And when the system is at equilibrium, so once you reach the equilibrium, this will not change anymore. You see, when you approach the equilibrium, you keep going up, going out, or going up, and then it will not change anymore. This is why you have a maximum. So in that case, you maximize the entropy of the universe. So this will always be a maximum. And therefore, correspondingly, if you use language of availability, A will be a minimum. Okay, so if I want to find the equilibrium, this gives me a powerful tool. I can, to find the equilibrium, I need to minimize A subject to some constraints. My thermodynamic system will have some constraints. So I need to minimize A. So therefore, if I want to find the equilibrium, I need to minimize A subject to appropriate constraints. Okay, so let's see what are the constraints. Let's first, what do we need? We need this line here. So I will copy again. And then, yeah, we want this. Okay, so we know what we want to do. So let's start. So this one will be, okay, so this is what we need. I will need it for several different cases. Okay, case one. Suppose we have constant entropy and constant volume. So suppose we have a constant entropy and constant volume. What do we optimize? We know we always have to minimize A subject to this constraint. Okay, so what do I mean? I mean the system entropy cannot change. The system volume also cannot change. So I look at my dA. So my dA is du minus p naught plus p naught dv. dv cannot change. This will be 0. And ds cannot change. This will be 0. So I have this. This is 0. Sorry. So dv is 0. This is 0. This is 0. Okay. So the minimization of dA, I want to minimize dA. This has to be the same as minimizing the internal energy. Okay, so for case one, if I have constant entropy and constant volume, my analysis of the availability tells me I need to minimize U. Okay, so this is the appropriate thermodynamic function to minimize. So let's have a look. This is the first line here. Is it correct? This one is not necessary. Right. So remember, constant entropy, constant volume. I need to minimize U. Okay, so this is what I get. Right, constant volume, constant entropy. I need to minimize U. Okay, I'm going to do a couple more. I don't want to do all. You need to know how to do all. Okay, so now we are going to pick another constraint, another set of constraints. So now I'm going to pick constant entropy again, but this time I want constant pressure. Okay, constant pressure. Now I will have constant entropy. I will have ds equals 0, and constant pressure I will have dp equals 0, and then the pressure will be the same as the pressure of the atmosphere. Okay, I open my thermodynamic system to the atmosphere. Right, so in this case, what do we have? Look at dA. My dA will be du, and dP is 0, and sorry, I will have this P naught times dV, and the last term will be 0. Okay, and this is what we want to minimize. Here you need to think a little bit more, because this is not at all obvious what is this thing on the right hand side of the equality, du plus P naught dV. Okay, now I claim that this is actually the enthalpy, related to the enthalpy, dH. Why? Because now let me write the enthalpy, the definition of the enthalpy for you. So from here, I know dH is du plus pdV plus vdp. Okay, and I know this dP is 0, this is 0. And then pressure is further, we have P equals P naught. And therefore dH is du plus P naught dV. And therefore, in this case, I need to minimize the enthalpy. Okay. Now you can repeat. So here, this is now this is here. We want to minimize this. Okay, now I'm going to do just one more. I'm going to skip the Helmholtz function. You have seen Helmholtz function today many times. Let's look at Gibbs. Gibbs you haven't seen much, so you can practice. You can do the Helmholtz function yourself. Now, if I have constant temperature, constant pressure, I will have to minimize the Gibbs function. Okay, remember this result. Now, first, you will see it soon, and second, you will use it a lot next week. So please remember. So if I have, we are not going to come back to availability anymore. Availability is a general way for us to conclude this result. So next week, we are going to do a lot of minimization of Gibbs. Okay, so I copy it here. So this is what I want. So this is case 4. So what do I have? I have constant pressure, so constant pressure and constant temperature. Okay, so I use my atmosphere to maintain this constant values. I use my surrounding to help me to reach this constraint. Okay, so actually this is the best is let's look at the definition of Gibbs. So this is Gibbs. Gibbs is related to enthalpy by this line, and the enthalpy is further related to the internal energy like this. Okay, and therefore this is actually straightforward. I will have dg is du. I will do the differential, and then I will have p naught dv plus vdp, but I already told you dp is 0. And likewise, I will have another term which is minus t naught ds, and then another term is minus t ds. I already say sorry, s dt. Dt is 0, so the other term will also be gone. And this is look at this. This is this guy here. This is exactly dA. So I need to minimize. Gibbs. Okay, so this is actually kind of easy. Okay, this is case 4. Yeah, this one. And actually, the last one is also cool. Let's just look at the fifth case. Case 5. Now, case 5, how do you do it? Case 5 on that table is actually coming from this constraint. So suppose the system is further thermally isolated. Thermally isolated from the surrounding. Now, originally I allow heat exchange. Now I decide to cut off this possibility. It's thermally isolated from the surrounding. Okay, so there is this picture. This picture, right? Originally I allow heat exchange, but now I do not allow heat exchange. So this is my system, which is isolated from the surrounding. So what should I get? Actually, we better get something familiar. We shouldn't have to do it from availability, but if you do it from availability, it should be consistent. Okay, so in this case, I also want the volume to be a constant. That is to say, I do not have any way to interact with the surrounding. I cannot exchange heat. I cannot exchange volume. Okay, so heat cannot enter, and I cannot do mechanical work. What do I get? I will get du is 0, right? Du has two parts. I cannot change the internal energy at all because I cannot perform work. I cannot inject heat. Okay, and then and this is dV is 0. Okay, so what is my availability? My availability here, up here is du plus P naught dV minus T naught ds. This has to be less than or equal to 0. Okay. So du is 0, dV is 0. The only thing I can do is T, and T temperature is always positive. So this inequality tells me the entropy can only increase or stay 0. So this is just a statement of the second law. The reason I recover this statement is because I make my system the new universe. Right now, I cut off the surrounding, so the system itself is the universe. So for universe, the internal energy is a constant, and the entropy cannot decrease. This is how we arrive at this point. Okay. All right. So this is that's it about this equilibrium. So I also gave you this one. So the last line tells you need to maximize the entropy. Okay, so you get all this. Just try this yourself. Okay, let's see how far I can move forward. the last part of this chapter is a set of equations called TdS equation. So that is to say, I can have a set of equations with T times ds on the left-hand side and then expressed like this. Now this is a set of equations. They are very powerful. You can use it, of course, for more calculations. That's why I put it here in the chapter of analytical thermodynamics. I could have talked about this earlier. Okay, maybe you should know why I do it here. One reason I do it, I put them here is because I would like to first learn the Maxwell relations before I introduce this. Once you know Maxwell relations, you know you can manipulate partial derivatives very quickly, and therefore it will be a lot easier to prove these equations, arming with the knowledge of Maxwell relations. That's why I put it here. And also, this is really something for a lot of calculations, so it goes well with the analytical part of this course. Analytical thermodynamics. Okay, so why do we care about T times ds? There is one question before the break. I kind of answered this, but I'm going to say again here. All right, so if I have a process, right? Why do we care about TdS? Why single this out? T times ds. That's because if you have a process, so for a reversible process, this directly tells you the heat exchange in the reversible manner. Okay, so if you know this, if you further know the temperature, this equation tells you how to get the change of entropy. So you can also obtain delta S by integration. Okay. Now these are not really quite new. You have seen this before, right? But what is the new elements here? The new elements are this. If you look at these equations, this on the left-hand side is what we want. We're talking about this heat, reversible heat transfer, how to obtain this change of S. Now, but first, you need all these equations. And if you look at the right-hand side, you find that everything on the right-hand side are experimentally accessible. So the right-hand side of this equation, these are from the notes. All right, so equation 551 to 553 are heat capacity at constant pressure, heat capacity at constant volume, and you hopefully already know what I'm going to talk about. What are these differentials? These differentials are related to compressibility and thermal expansion. Okay, so these are experimentally friendly. Okay, so we are going to try. We're going to derive these equations. So here, I'm going to call this TdS1. This is TdS2, TdS3. Okay, I'm going to derive 1 for you. You are going to do 2, and if I have time, I will do 3. Okay. And you should also appreciate this set of equations a bit more. This you can view this like that, right? This is you can view this as originating from S, when S entropy S is given in terms of V and T. The first one is the most useful, and likewise you have P and T. And the last one is P and V. So for PVT system, if you know how to obtain the entropy as a function of these variables, you'll be able to choose the appropriate equation to do the calculation. Okay, so now let's derive the first equation. Okay, so the first equation I will write as, suppose I know as entropy in terms of V and T. Then I can write ds. This is not surprising. This is the starting point for this. Right? S in terms of V and T. So I will have V dt plus V dV. Okay. So this is S is a function of state. So if S is given in terms of V and T, so the change in S is driven by the change in the temperature and the change in volume. Okay, so what I want is TDS. So let's make it into TDS. I will have TDS. Okay, so let's see how to manipulate this term here. We know before that if I have heat capacity at constant volume, this is related to this result at constant volume. And if you write out the first law, you will very quickly see that this is related to this guy. Okay, you write down the first law, you have TDS minus PDV, and then the PDV term is gone, and then you do the derivative, you get this result. Okay, and therefore you already see this term here. So T times this guy will give you CV. All right, so this term is done. So I will have CV dt. Okay, so this is this guy. And the second one, let's try the second one. Let's play a little bit with this. So T times this partial derivative, I will just apply Maxwell relation. So one of the four Maxwell relation tells me exactly this derivative. So as with the partial S derivative of S with respect to volume at constant temperature. Now, if you check that table, you will find this result. Okay, so this is one of the four Maxwell relation. You just have to trust me. So this is Maxwell. Okay, so this is what this is this guy here, the second term in this. So I will have T partial P partial T times dV, which is this one here. Okay, so let's make a note here. So this is Maxwell. So this is done. Okay, so you can proceed to look at the, you can derive the second one and the third one yourself. One of these is in the assignment. Okay, so just trust me, they are correct. Okay, what else can we do? What else we can do is this. I'm going to write it in a way. I don't have much time, but this is really something fun. So I want to do it now, and hopefully you can have something to think about over the weekend. So this is TDS equation. And again, the next part I might overrun a bit, so you are welcome to leave, or you can watch the video later if you are busy and you need to go. Okay, so first let me write it in terms of compressibility and thermal expansion. Okay, so this is to really show you everything is experimentally accessible. Okay, so this line I can change this a bit, and this is this ratio beta divided by kappa. Okay, so this this requires a few more lines. You have done it. You have shown this before, so I will just use the result right away. And this one is minus TV times beta dP plus Cp dt. And the third one is Cv kappa beta plus Cp 1 over beta V dV. Okay, so just in case you don't remember, so this is beta is defined as the fractional change of volume when you change the temperature. So this is related to thermal expansion. And kappa is compressibility, is defined with a minus sign. And it's the change of volume with respect to pressure. Okay, and then from these two, you should be able to find out this. All right, this is the reciprocity theorem. Okay, so and then this is one. Okay, up to now it's kind of general. I just rewrite the TdS equation in terms of beta and kappa. And from now on, I want to do something specific. I want to use the ideal gas result. So the ideal gas you can show. So for the ideal gas, in green color is specific. So for the ideal gas, can show beta is 1 over T and kappa is 1 over P. Okay, so this is a specific result. Okay, so I just want to play a little bit with the TdS equation for you to feel a bit happy about this, because it might look very random that we introduce this, but at least one thing we can do is to show that they are correct. Okay, that's to say, we learned this ideal gas result from long time ago, and then we derive this today. So from the result of this ideal gas, we should be able to get something that you can recognize, so you know that everything is logically linked together. So I'm going to plug in this result for TdS1 and let's see what we get. So for TdS1, what is TdS? When I have an ideal gas. So when I have an ideal gas, I will have T, and beta is 1 over T. Right? Beta is 1 over T and kappa is 1 over P. So this becomes P divided by T. Right? And I will have my dV. And this is your old friend again. What is CV times dt? CV times this dt. This is a big warning I gave long time ago, and I briefly mentioned this today. Waiting for this moment. And CV times dt is du. Okay, why? Why? You need to really check back my notes. Okay, so I can have this result. Okay, done. This is what I want to show you. Now, you see, I just plug in the ideal gas result and just rearrange it, and I will get to this line. And you will ask, what is this? What is the relevance of this line? Okay, I will tell you what is the relevance of this line. So I can cancel T. So I have TdS, I have PDV, and I have du. So I just rearrange. I will have TDS minus PDV. So this is my first law. So basically, I correctly obtained the first law. Here, there's no reference to the first law. I just applying the ideal gas result, and I will be able to get something you recognize. You better, hopefully at this point, you will just say, I know this line. This is just the first law. Okay, and for the TDS2, I can play the same trick. So let me try it. So for the TDS2, TDS2 is also very fast. So TDS2, I will have TDS. Then I have this. This is TDS2, TS2, TS1. Okay, I have minus T. And what is this thing? This partial derivative. This is V times beta, V times beta. Okay, and beta is 1 over T dP. And I have this Cp dt here, and this using the same argument. This is actually dH, identical argument related to Joule-Thomson experiment, and you get this result too. So this thing is just this product is just dH. So I will have TDS minus. I get rid of my T, so I will have minus VDP plus DH. And what is this? This is again something you recognize. You know this better be true because you learn it somewhere. This is based on the first law, and you introduce something new called the enthalpy, and you do the differential, you get this result, and you know this is also correct. All right. I have more to say. I can do for TS3. I have something else I want to show. So TS3, I will want to show something, and I will show it next week. But this is also, this is already enough. Okay, so TS3 is a bit longer. I will do it on Monday when we meet next time. Okay, thank you. And this is the end of today's lecture.